Hello, statistics students. I want to give you a little lecture on starting chapter 11, which you will need for the next homework assignment. The next homework assignment, homework 12, is posted on Canvas under week 13. It's due April 6th, and I'm going to give you two little lectures on chapter 11, and this is just the first one. So stay tuned, there'll be a second one sometime soon. All right, so this goes with the PowerPoint that I'll post a link to. It's called Chapter 11 Model Checking. And so I'm going to kind of follow along with that and tell you which slides I'm at. So the first slide says we're in Chapter 11. We're doing model checking and refinement. There is code for this in the Canvas module. There's going to be two sections of code. The first is Chapter 11A. That kind of is going to walk through what we're doing today, which focuses on the first case study in Chapter 11. There will also be a Chapter 11B, which will focus on the second one. So on slide 2, we learn about this study. So the study is about whether men and women metabolize alcohol differently. And so having like the same number of drinks and even being the same size, women have less alcohol tolerance than men. And this study is trying to look at whether that's because there might be an enzyme in the stomachs of men that's more active at breaking down alcohol compared with the enzymes in the stomach of women. And one way they could test that is to compare how different the blood alcohol content is when they inject the alcohol directly into veins. So then it wouldn't be broken down by things in the stomach. So you'd kind of like get rid of that effect of the potential enzymes in the stomach. And then you could compare that to what happens when you drink the same amount of alcohol. And presumably, if you just inject the alcohol directly into your veins, you're going to have a higher blood alcohol content than if you drink it and then your stomach breaks down part of it and then only part of it goes out into your blood. And the idea is that that might happen more for men than for women because they have this enzyme that maybe is more active in their stomachs. So that's the idea. There's also this variable that has to do with whether they're an alcoholic, and that might play in because it might be that like alcoholics' enzymes have adapted to dealing with alcohol and they've increased their tolerance. So maybe that's an important variable as well. So we're dealing with this situation where we have their alcohol metabolism, the amount of the enzyme, their gender, and whether or not they're alcoholic. And we have two things that are quantitative variables, the amount of alcohol in their blood, their metabolism, and the amount of enzyme in their stomach. And then we have two things that are categorical, their sex, and whether or not they're alcoholic. So that's the deal. On slide 3, you can see the header of the case study. We have the subjects, we have their metabolism. So that's looking at the difference between when you just injected it in their blood versus when you let it go through their stomach. So that's the metabolism rate. The gastric is the amount of this enzyme in their stomachs and how active it is. And then the sex is the sex, and then the alcoholic is whether they're alcoholic or not. So we're going to kind of walk through some steps with this study. The first step, so I'm on slide 4, first step is look at the graphs and decide whether you need some transformations. Maybe we need a log transform or a squared term or something like that. We need to make sure that with at least the two quantitative variables, we're dealing with a linear relationship here, and there's some reasonable equal variance assumptions. Then we're going to make a basic model to start with and look for outliers and see if those outliers are really affecting the results. And because this is in the chapter about outliers, probably there will be some. Yay! Okay, so once you kind of look at the outliers and you figure out what you're going to do with them, then you're going to do some model refinement. And this is hinting at what's going to be like all the fun of chapter 12. Chapter 12 is like all about model refinement. So we'll be dipping our toes in that, but there will be more on that later. All right, so moving on to slide 5. Here's our picture. This is a cool kind of plot. We haven't done this before in R. It's in the code. It's a lattice plot, so we can kind of look at the alcoholic men and women and look at them separately. And if we just look at this plot, it doesn't look like whether or not they're alcoholics really makes a difference. And there's like not very many alcoholics in the study. So if it did make a difference, it would be really hard to tell what the difference was going to be. So the plan here is to ignore that variable for now and then add it back in later and see if we were justified in ignoring it. Okay, so slide 6 kind of just looks at the data in a slightly different way. It looks like if you just look at the blob of points over sort of in the bottom corner, they're more or less linear. There's not a problem with equal variance. There are these possible outliers, points 31 and 32. I say that because they're far away from the rest of the data. The gastric levels are like between 4 and 5, whereas all the rest is below 3 or so. So we kind of don't know what happens between 3 and 4. There's really not any data in there. It looks like those points might pull the lines up when otherwise the slope of the line might be a little bit less steep. If we look at this, one other thing we can tell is when we look at the triangles, which are the females, versus the circles, which are the males, it looks like if we visually ignore points 31 and 32, it looks like a line with the same slope would kind of go through the triangles and the circles. And that turns out to be important. So we'll go on to slide 7. We'll start with a basic model. I'm ignoring alcoholism for now. Here's my basic model. Metabolism is predicted by gastric, so that's the enzyme. Sex, so that's going to be a categorical variable. In this particular case, 0s are female, 1s are male. And then the combination of gastric and sex, so maybe the amount of how the enzymes affect your alcohol metabolism depends on your gender. So that's what that last thing with the colon is. So I run this model, and then since we're focusing on outliers, the first thing I'm going to do is go and look at the outliers. So this next slide, slide 8, has my model, and it has the outliers plotted. I just did plot my model. And here it has the standardized residuals on the y-axis and their leverage on the x-axis. And the key thing here is these red dotted lines. And those are estimates of the Cook's distance. So when the Cook's distance, this is a thing that's calculated by R, when it's 1 or bigger than 1, you know your points are having a big influence on fitting your model. So when I look here, I can see that points 31 is like down in the bottom corner, and that has a Cook's distance like right around 1. If that was the only outlier, I might be like, a Cook's distance right around 1 isn't that big of a deal, but it's like still really far away from the data. But then point 32 has a Cook's distance of even more than 1, and that's like really alarming. So both of those are probably not useful to have in this data set. So the next step would be figuring out how big of an effect they have in the model. So if we go to slide 9, we have several different ways of measuring outliers, and the book kind of goes into like the gory details of how you can calculate these. Given all the things in our lives right now, I don't think it's that big of a deal that you know how to calculate all of them by hand. Like, this is a thing that your computer program knows how to do. It gives you the Cook's distances, and that's fabulous, and you can kind of go from there. But if you want to look, it has the details, and they're kind of cool. So there's 3 main ways. Leverage is really interesting. Leverage is looking for points that have unusual predictor values, and this can be especially important when you have many different predictors. You might not notice that the combination of predictors is unusual. So that can sometimes have a big impact on the estimate of the slope, and you may or may not notice it if you have like 10 possible predictors, and like particularly I'm thinking about climate predictors. Like there's very few places that are like super, super hot and super rainy. And so if you had a place like that, you might not notice it because there are places that are hot, there are places that are rainy. It's the combination of being super hot and super rainy that's weird, and you might not notice that on a plot, but your leverage is going to pick up that point and see how it's going to affect your results. So there's leverage, there's studentized residuals, and the idea is here you standardize the residuals. And remember, the residuals are supposed to follow a more or less normal distribution. So Once they are standardized, so you take how far the point is away from the line, you divide it by the standard deviation, most of them shouldn't be farther away than 2 or minus 2 away from the line. So about 5% should be. So if you see studentized residuals, a lot of them, or even just a few that are like way bigger than 2 or minus 2, that's a big deal. Cook's distance is the most useful single way of measuring outliers because it measures the overall influence. And they calculate those on page 325. R automatically calculates them. And the idea is, just like in the previous example we looked at, if they're around or bigger than 1, they're having a big influence on the regression. So you need to start paying close attention to them at that point. So let's go into slide 10. Slide 10 has this fabulous display chart that is on page 321 in your textbook. And the idea here is like, what do you do when you have outliers? So step 1 is, does it actually change the conclusions? If no, whatever, fine. You're getting the same thing with or without them. Like, don't agonize over what to do with them. If they do change the results, now you start to have to think there's something going on. So the first thing you can do is say, is this really a reasonable part of my sample? Maybe it belongs to a different population. Like maybe maybe all of my sampled individuals in this alcoholism study were ages 30 to 40, and these 2 happened to be like 80-year-olds, and they just metabolize alcohol differently, and maybe I should restrict my scope to only really talk about people in the age group that I have data from, and say, like, I don't really know what's going on with 80-year-olds, I need a bigger sample to tackle that. So if there's some reason that maybe your outliers are coming from a different population, you would omit them. You would probably also, it doesn't say this in the chart, you would also probably restrict your scope of inference and say, well, I omitted them because they came from a different population, and now I really can't talk about that other population. If they really do come from the same population, now you have to figure out what to do with them. If they have a big impact on the regression, you really have to remove them and proceed, particularly if that's the conservative thing to do. So you might want to think about the balance of the societal effects of a case 1 or type 1 and type 2 error. If they're not having a huge effect, you might want to like dig into figuring out what's going on, but you don't have much you can do about that. So that's what's going on with this particular flowchart. So let's go back to our example here. We were looking at the gastric alcohol stuff. So points 31 and 32 were the outliers that had a really high Cook's distance. So what we're going to do on slide 7 is we're going to try modeling it without them. We're going to see whether they have an effect on our conclusions. I try modeling it without them. That's my LM2 here. I look at the Cook's distances again. I see magically they're gone. So there's not points with high Cook distances anymore. Great. I mean, that was the point, right? So then the next slide, slide 12, compares my results with and without them. So on the left, I have my results with them. And one thing to note is with them, the interaction between gastric and sex is significant. It has a p-value of 0.0118. Without them, my interaction is not significant. It has a p-value of 0.1885. So indeed, it does change my interpretation. And if we go back and we look at that original plot of the data, it's actually not surprising that they pull the line for the males up so that it's different from the line of the females. And that's what that interaction is telling me. With those 2 outliers, the line for the males would be pulled up and it would have a steeper slope. And without those 2 outliers, the line for the males would be pretty much parallel to the line for the females. And you can see that pretty clearly just by looking at the plot. Okay, so this is a big deal because my outliers do affect my interpretations. And I am not comfortable with reporting results that hinge on just 2 observations. If there's really a difference between the men and women, I really want more than 2 points to be telling me about that difference. So I'm going to go forward excluding those points. And that also means that when I state my results, I'm going to say that they only apply to the gastric enzyme levels of up to about 3. I don't know what happens at those higher levels because I excluded my outliers at those higher levels. All right, so we'll go on to slide 13. Now I want to go back and see whether alcoholism matters. So I can make a full model with alcoholism and a reduced model without it, which is the one I just looked at. And now I'm going to do an extra sum of squares F test to compare them. So here I have just my code for doing that. The ANOVA red model, comma, full model is where I'm going to run my extra sum of squares F test. And if I look at slide 14, I can see the p-value from that was 0.93. So that means there's no evidence that I need to include this variable for whether or not they're alcoholic. So whether or not they're alcoholic doesn't seem to have an impact on how gender and enzymes affect alcohol metabolism. So no, I can ditch alcoholism from the model. It doesn't seem to matter. I can go on to slide 15. Our full model without the outliers, we already looked at it. It had this interaction between gastric and sex male with a p-value of 0.1885. I think I can drop it. It's a pretty high p-value. I might be able to get better estimates for the other things in the model if I drop it, particularly the effect of gender. It's kind of looking like gender isn't important because both of those terms are non-significant, but if I look at the graph, I can tell it probably is important. So maybe by having this non-significant interaction, I'm making it harder for myself to see that. One thing to notice is this is the same model that's listed on page 329 in your textbook, but they're modeling males as the base case and females, and I'm modeling females as the base case with males, so it's slightly different, but it's the same basic model. All right, so we'll go on to slide 16. I dropped that interaction, and look, now gender is really significant. So it went from having a p-value of 0.79 with the interaction. Now I get rid of the interaction, and it has a p-value of 0.000139. Cool. So now I can see this thing that I had already seen in the graphs as important. I can look at these partial residual plots. These are on slide 17. These are cool because they allow us to look specifically at the effect of one thing accounting for all the other things. They're not super critical in this particular model because we don't have too many things to visualize on one graph. But in some cases, if you have like 5 or 6 predictor variables, you can't symbolize them on one graph and visualize them, and you really need the partial residual plots. So let's look at them in this simple case. On the left, we're looking at the response of the metabolism to gastric enzymes after having accounted for sex. And we can see that even after having accounted for sex, it does look like the gastric enzymes matter. And on the second, we're looking at the effect of sex after accounting for the gastric enzymes. And you can see that even after accounting for the effect of gastric enzymes, it does look like sex matters. So that's cool. We can kind of zoom in on just one of the variables, even though we have multiple variables in the model here. All right, let's go on to slide 18. We can look at a beautiful graph fitted using this model that we just looked at. One thing to notice here, when I made my graph, I kept my outliers there, but I made it so that the model clearly doesn't go to them. So my model only makes inference for gastric enzyme levels up to 3. And I don't plot the points beyond 3 because my model doesn't apply to them because I excluded them from the model because they were outliers. So you really want to make sure you only plot your line for things that legitimately you modeled. So that's useful. That would be like the model you'd want to present in your homework. Now, one thing, let's go on to slide 19. One thing, if we look at this original graph, there's some possibility that we could have forced the intercept of these lines through 0. It makes sense that if you don't have any of this enzyme that breaks down alcohol in your stomach, it's not going to break down any alcohol in your stomach. And so the levels should both be 0 probably together. So it would be reasonable to force the intercept through 0 here, particularly for the males. No, particularly for the females. So the females had a higher line. If we go to the previous slide, the females line is this red one, and it's generally lower than the males. So if we force the females through 0, we might get a simpler model, essentially. So on slide 19, we have my code for forcing the females line through 0, and I can do an extra sum of squares F test and see if that was well justified. And if you go to slide 20, you have the results of my extra sum of squares F test. It appears that it was well justified. So the p-value is 0.94, saying I don't need the more complex model with an intercept for females. I can use the simpler model. And they talk about this in the book a little bit on page 329, if you want to read all about it. So I get this final model here with males and females, and here I can calculate the coefficients. I can calculate the metabolism for males. I can say males had a higher first pass metabolism after accounting for gastric activity, and the p-value there is the p-value from the second line, the 0.0003. And then I can also calculate how the mean for the males differs from the mean from the females. It's 2.2 times the mean of the females, and I talk a little bit about how to calculate this on page 329 as well. So I hope that's useful. It's an example that shows us how to look for the outliers, how to interpret the Cook's distance, how sometimes you have to restrict your scope of inference and omit the outliers. So here we restricted our scope of inference to gastric enzyme levels less than 3. We omitted those 2 points. And then how to do some model refinement with some extra sum of squares F tests, which is what Dr. Chan talked about last week. So that should be review for you. So the next time I will go through the next case study a little bit. You should have enough to start tackling your homework, although I know you're probably pretty busy with your case study about the wages at Weber State. I hope you're all doing well. I'll talk to you soon. Bye.